So hello and welcome back. This is our final lecture in the Probabilistic Robotics series, Lecture 22C. And it will be an introduction to recursive Bayes filters framework for estimating the state or belief of a system given a sensor and action model. We will review using Markov assumptions for estimating the probabilistics of the states for a system or the world. And we will create an explicit representation of uncertainty to represent a robot acting in the real world as opposed to what would happen with a simulation, which we know would not have challenges or uncertainty. And we will formulate the perception problem as state estimation and actions as a utility optimization. Recall that some of the slide content as well as the course content comes from the work of Wolfram Burgard, Sebastian Thrun, and Dieter Fox in their work Probabilistic Robotics, Intelligent Robotics and Automation series. If you want to know more about their work, please check out probabilisticrobotics.org. So, looking at Bayes filters framework, if we have a stream of observations C or measurements from a sensor, and we have a robot action data U, then we call this the data of observations, or the given, where we have U1, Z1, U2, ZT, etc. Assuming the robot has an action, then we take a measurement. The robot does another action, we take another measurement. Thinking of this in the context of the door, the robot makes a closing motion on the door, we take a measurement of the door, the robot makes another action, we take another measurement of the door. So our sensor model is that now the probability of a state X, the probability of a sensor measurement given a state X, or the action model is the probability of a state given an robot action and the previous state. The prior probability of the system can then be represented by P of X. So if we want to estimate the state of a dynamical system, then using our Bayes rule, the posterior of the state is called the probabilistic belief of the state of the system. So we represent this as Bell of XT, or the state of the system at the current time, is now dependent upon the states, the actions, and the measurements of the robot for the previous times up to the current time. So that means the belief of the state at time X is going to be the probability of being at time X given the actions and the states of the system up to and including that current time. So with the Markov assumption, we can model this equation with this diagram here, where xt minus 1, xt plus 1 represents the current state of the system or the robot as it's moving through the world, where after each action of the robot and each measurement, it moves to the next state. So we have to make a few underlying assumptions in order to simplify the mathematics. The first one is that we have a static world. So we're going to assume that the world is not changing, and that we're going to be independent of noise, which could be from sensor error or motors or the robot. And we know that there is no perfect model, and that we're going to have some approximation errors, but we're going to assume for now that we have a perfect model, so we're not going to worry about that. And then we're going to simplify the mathematics by using our independence assumptions. So we're going to use the fact that the probability, so using all of these assumptions, these underlying assumptions, we're going to have that the probability of a certain sensor measurement at time t is dependent upon the state from 0 to t, the sensor measurements from 1 to t, and the robot actions from 1 to t. And we can simplify that down to the probability of a sensor measurement at time t is dependent upon the state at time t. And the probability of a state at t is going to be dependent upon the states 1 to t minus 1, sensor measurements 1 to t, and robot actions 1 to t, which if we use independence, that gets simplified to the probability of the robot at state t is only dependent on the previous state t minus 1, as well as the input at the action at time t, and that's what this diagram shows us here. So now the derivation of the state belief will be based upon Bayes' rule, where the probability of A given B and E, where you know that's now going to be our actions as well as our sensor data or measurements, is going to be the probability of B given A and E times the probability of A given E divided by the probability of B given E. So we can use this to derive the probability of the state at time t given the u1, z1 to ut, zt by making substitutions. So we would let a equal xt, b equals zt, and e equal the action inputs u1 to ut and z1 to zt minus 1. And so now we can rewrite that Bayes rule in terms of that probability as the probability of xt given u1 and z1 to ut, zt is the probability of the measurement at t, the state at t, u1 to ut, z1 to zt minus 1, times the probability of state t given the actions u1 to ut and the measurement z1 to zt minus 1 over the probability of measurement t given the actions u1 to ut and the measurements z1 to zt minus 1. So if we look at that bottom equation, the probability of zt given the states, the inputs, and the previous measurements, we know that the current state cannot be independent of previous measurements and controls. However, we know that xt exactly is based upon those previous measurements and those previous controls. Therefore, we can disregard all of those values because since we know xt, we know it would lie on those. So as long as we have xt, we have those values. So then in that case, the denominator will become a constant independent of all xt, and it can be normalized as we did before by creating that normalization constant eta. So we can now simplify this to be the probability of the current state xt based upon u1, z1 to ut, zt, the previous actions and measurements, is now just eta times the probability of the measurement t given xt times the probability of the state t given u1 to ut and the measurement z1 to zt minus 1. Now we need to do another simplification by using marginalization to simplify the probability of the state xt given the controls u1 to ut and the measurements z1 to zt minus 1. So recall that marginalization stated that the probability of x is the probability of x and y over all possible values of y, which can also be written as the summation of the probability of x given y times the probability of y, summing over all possible y's. So we're going to do another A, B, E substitution. So we're going to write this in terms of A, B, and E as the probability of A given E prime is the summation of over all B, the probability of A and B given E prime, or that can be written as, using marginalization, the probability of A given B and E prime times the probability of B given E prime. So doing an A, B, E substitution like we did before, we get that the probability of A given E prime, where we let A equal xt, B equals xt minus 1, and E prime be u1, z1 to ut, zt, becomes the probability of xt given u1, z1 to ut, zt equals eta times the probability of the current measurement time at the current state time times the summation over all xt minus 1 of the probability of xt given xt minus 1 and u1 to ut and z1 to zt minus 1 times the probability of x at t minus 1 given x of t minus 1 and all of the controls u1 to ut and the measurements z1 to zt minus 1. So looking at this equation at the top here, we can make another independence assumption by saying x is independent of all of the u's to the left of u of t minus 1. So in other words, the current state should only depend on the current input. Anything before that would have depended on the previous inputs. So we can get rid of all the variables before t minus 1 because t was created from those. So by doing that simplification, this equation now becomes the probability of xt given u1, z1 to ut, zt is equal to eta times the probability of the current measurement giving the current state times the summation of all xt minus 1, the probability of the current state given the previous statement and the current input control ut, times the probability of the previous state x of t minus 1 given all of the inputs u1 to ut and the measurements 1 to t minus 1. Now we need to make another independence assumption to get rid of that ut so that we could then actually use recursion or a computer to solve this problem. So to make another independence assumption, we can say that x of t minus 1 is independent of ut. So the probability of the current state xt currently is, it depends on u1 z1 to ut zt. And we can write that as eta times the probability of zt given the state t, so that's the sensor output given the current state, is the summation of all t minus 1 from the current state given the previous state and ut times the probability of the previous state given the previous controls and the previous measurements. And remember, we can make this assumption because we can assume that the previous state should not depend on the current input, because that would be looking into the future and it hasn't happened yet. And so finally, we can write the belief of the current state of the robot as the normalization constant eta times the probability of the current state measurement given the current state times the summation over all those previous states up to t minus 1 times the probability of the current state given the previous state and the current control ut times the belief of the previous state x of t minus 1. Oh, a lot of math. I hope you followed. Please watch it again if that was a little difficult for you. So let's look at the intuition of some of what we did here. To estimate the state of the robot in the world or the location of the robot, you have to use a belief of where the robot is based upon a probability distribution. It's easier to kind of see this in a discrete case. For example, estimating the location of a robot in a grid cell in a grid-based world. So we know that we believe the robot was previously at the state t minus 1. And if we know how the robot moves in the world, we can then come up with a belief on where the current cell is based upon controls and sensor observations. It's kind of what you do when you do localization. So the behavior of the robot can then be found by using the previous state summed all the way up to the current state, given the previous state and given the current controls. So if the robot takes a measurement and we know its previous state and we know the controls, then we can determine with the normalization constant our belief of where the robot currently is in the world. So using that intuition, we now can write the belief of my current state equals eta times the probability that I'm in current state x given my current measurements, that's called our correction, times our prediction, which is the summation of all the previous states, t minus 1, is the probability of my current state x, given the previous state, t minus 1, given my current controls, times my previous belief. I think the easiest way to think about this is that I have a robot in a certain cell, and I know where that is, and that's my prediction, my belief, and I know that I have the robot move forward one cell, and I take sensor measurements again to confirm that I really moved forward a cell, then I can make a belief that the robot has moved one cell north, right? So these are the kind of things we use for localization and mapping to determine where the robot is in the world. What's my current belief? What's my current sensor data? What kind of input did I give to the mobile robot? The robot then moves. I read the sensor data. I know how my control was enacted. What cell do I think I'm in now? And so we call these Bayes filters, where we have the observation Z, the action U, and the state X. So the belief that I am in the current state T is the probability I'm in the current state T, and U1, Z1, where that is all of my inputs and my sensor measurements up to that point. Then what we did is we simplified this by using our normalization constant, where we multiplied the probability that I am in sensor at time t given x and u and z up to time t, and the probability that I'm in state t given u and z up to time t. Then I used a Markov assumption in order to get rid of some of those previous states, so that I now only have eta times the probability of sensor t given the state t, because I know any previous states would have dependent upon those, because I know that any previous controls or measurements would already be accounted for in xt, times the probability of the current state t for u1, z1 up to ut. So then using my total probability assumption, I would have eta times the probability of the current measurement t given the current state, xt, and the integral of the probability of xt given u1, z1 to ut xt minus 1, and the probability of the previous state t minus 1, u1, z1 to ut dx of t minus 1. So I then make another Markov assumption of independence in order to get rid of some of these terms. And I can now write this as the probability of the measurement t given the state t times the integral of the probability of the state t given the input at time t and only the previous state, none of the other ones, input controls, and the probability of x at the previous time t minus 1 given u1, z1 to ut. So now we make another assumption, another independence assumption in order to get rid of ut, because I know that the control input at time t should not affect the previous state t minus 1. So eta becomes the probability of the current sensor reading zt at state given state xt is the integral of the probability of the current state given the current control and the previous state times the probability of the previous state t minus 1 based upon all of those inputs up to, and sensor readings up to t minus 1. So I eliminate the control at time t. And finally, this equation becomes the eta times the probability of the current sensor measurement, the current state times the integral of the probability of the current state given the current control, the previous state, times my belief of where I was for my previous state over the derivative of the previous state. And this was all to get us to the belief of xt by making several assumptions using Bayes filters and Markov independence assumptions. And then what you could do in a computer is now we can do recursion because everything's now only based upon previous times. So if D is a perceptual data item Z, then you would do for all X, you would calculate eta plus that belief. And then once you get that belief, you would find those steps are used to make the normalization and the correction part of the equation. Or if you have an action item, you now would use steps 9 to 12 to do the prediction. So for all X, find the belief based upon that integral, or if it's discrete, based upon that summation of the probability of X giving you X prime times the belief X prime dx prime, which is based upon our previous state. So you would add those two together, and that will now give you an approximation for the continuous state, or maybe the sum for a discrete case of the robot's belief using recursion. So once again, this is the equation that we used, and we're now writing an algorithm in our computer in order to be able to come up with the robot's belief of where it is in the world or what action's been executed and the state of the world by using this sensor model or this perceptual model and this action model. So here's a very basic example of what this Markov localization would look like, where we have that the robot can sense that it's at a door when a door is open. So the first time the sensor pings, the probability of a certain sensor reading giving that the door is open, you see that the robot has an equal probability of a third at each of these doors, that it's beside each of these doors. So then as the robot starts to move, the probability will distribute as the robot travels along the doors, assuming it's moving down this hallway, until it pings at another doorway. And now we have the probabilities that the robot is at the second door, and we also have a probability that it has moved beyond that second door to the other two. If we now multiply these together, you will see that the probability that the robot is now at the second door, because that one pinged twice, whereas the other two pinged only once, at the bottom, we will see that the robot will localize at the second door, because whereas those other ones only had one sensor hit before the robot moved, you have a second one here. So in summary, Bayes' rule allows us to compute probabilities that are hard to assess otherwise. For example, finding the probability of Y by using just those summations and never having to find the probability of y. And then by using Markov independence assumptions and recursive Bayesian updating, we are able to efficiently combine evidence in order to increase our confidence of a certain state in the world in order for the robot to make a decision. And we know that these Bayes filters are really just a probabilistic tool for estimating the state of dynamic systems, and you will see this in the future. So this is our final lecture for week 2. I know week 2 has been intense. So just take lots of notes, watch the videos a couple of times, and I think it will start to make sense. And finally, have a robotacular day.